without it taking all night. Chapter 5, Fire Behavior. Um, should be a good old time. It would be cool to get some other people into these to talk about some stuff with us. But the three of us are cooler than anybody else in the department, so we'll just roll with that. Understanding fire behavior is absolutely crucial to successful firefighting operations. Got some sweet pictures here. Fire has been man's best friend as well as his enemy. You don't have to go too far back in history to understand that that's kind of where it all began, right? Keeps us warm, makes us food. And the importance of fire behavior. We want to understand fire behavior. It's critical that firefighters understand how fire behaves. Better decisions can be made. We can decide if this is going to be an interior or an exterior attack, depending on what we're doing, the amount of water we need to use, the required apparatus and equipment. So, defining fire. Fire is a rapid oxidation process with the evolution of light and heat in varying intensities. It requires fuel, oxygen, and a heat source. We're going to beat the fire triangle to death to the point where we should all pretty well understand it. I would imagine you guys got a pretty good grasp on the fire triangle. It's kind of something that we're kind of taught from the Boy Scout age, so ought to not be an issue there. Chapter goal, this lesson will provide the student with a basic understanding of combustion theory and how a fire behaves within a structure. We're going to go over the fire triangle and the fire tetrahedron. Talking about some measurements of fire and BTU, heat output. We're talking about some fuel characteristics. We're going to talk about some chemistry and physics related to fire. We're going to talk about fires in a compartment, fire growth and development in a room and contents fire. Vastly different than a wildfire, something that's outdoors. We're talking about explosions, and then we're going to have a summary, and hopefully there will be some sweet pictures along the way. If you don't enjoy fire, you're weird. Following completion, the student should be able to describe or demonstrate the following: parts of the fire triangle and the parts of the fire tetrahedron. Speaking of the fire triangle, here it is. The fire triangle is the basis of all fire operations, right? We have oxygen, we have heat, and we have fuel. Remove any part of the fire triangle and the fire goes out. So if we have a fire and we put water on it, we remove the heat by putting water on it. So we're taking that part of the triangle out, the fire goes out. And a lot of times in wildland fire, we may be doing some stuff that, with some tools where we might be removing the fuel. Maybe you're taking the fire fuel away, fire goes out that way. A lot of the fire extinguishers are removing the oxygen. So one way or another, when we fight fire, we have to remove one of these sections: fuel, oxygen, or heat. No matter what kind of fire it is, that's what we got to work on. The fire tetrahedron is fuel, oxygen, uninhibited chemical chain reaction, which is the actual burning process, and heat of ignition. Okay, the fire tetrahedron was designed to help people understand a little bit about some chemical fires, because that can be a little bit different, because I think we'll probably talk about it here, but some chemicals can burn without heat. So we have that uninhibited chemical chain reaction. The fire tetrahedron added inhibited chemical chain reaction to the equation. So fire begins to burn, chemical chain reaction occurs, breaks down fuels into new materials. Materials combine with free radicals, allows burning process to continue. So break in chemical chain reaction extinguishes the fire. So as most substances burn, they're actually breaking down whatever it is that's burning into into something that's combustible. So whenever wood, for example, burns, it's really breaking that wood down into a product of combustion that the gases is what actually produces our fire. So that's where it brings this into that part of that chemical chain reaction. If we can break that chain reaction, most of the time by removing one of those pieces of the fire triangle, then we can put the fire out. So we'll talk about some types of fuel. Within this, we should be able to understand the three states of matter, which you probably already do, those of you guys that hit some science classes. The terms endothermic and exothermic. The terms flammable and explosive limits. So solid, liquid, and gas is our states of matter. At least the states of matter that we're going to talk about for the for the sake of our fire characteristics. Solid, like everybody always uses water, so solid would be ice, liquid would be water, and then gas would be steam or vapor. Wood is no different. Wood is in a solid form, and then wood can give off a gas form, and that's what gives us our fire. The law of conservation of matter. Matter can be neither created nor destroyed, only transferred to a different state. Um, Again, science has not always been my best area of expertise, but that's the general concept of a lot of science is that you're never actually creating matter. You're just transferring it to a different state, whether that's uh, you know gas or solid, liquid, plasma, etc. So matter can be divided into two categories: organic materials and inorganic materials. Typically, organic materials will burn, and typically, inorganic materials do not burn. Um, let's see if they'll go into some more detail on that here in a little bit. So solids, molecules are tightly arranged. That's what gives them their density. Solid fuels must be changed to a gaseous state to burn. Like we talked about, whenever wood or plastic is burning, or most materials for that matter, you're changing the fuel characteristic to a gas, and then the gas is what actually burns, and it breaks down that solid into a gas form, and that's what actually shrinks the solid material as it burns. So the burning process, fuel must be in a gaseous state to burn. Solids must decompose or pyrolyze. Liquids must vaporize. Okay, so in an internal combustion engine, we think of the fuel that we put in it as gasoline or diesel, but what that fuel is actually doing as it's injected into the cylinder is it's being atomized into a gaseous state. Um, and then the density of that gaseous state can depend on, like the air-fuel ratio that it puts in there. But the general idea is, any of the solids must somehow convert to a gas, and any of the liquids typically will convert to a gas for them to burn as well. And it happens on a very microscopic level, so it's not quite obvious until you really think about it. Like you look at gasoline on the ground and you're thinking, oh yeah, that gas is burning, but really the gas is vaporizing or off-gassing into a gas form, and then the actual gas is there. The vapor is what's producing the combustion. So it's pretty well standardized. There are some exceptions, but for the most part, that's how a lot of this works. So now the different materials, however, will have a different ignition temperature. The ignition temperature is the minimum temp at which a fuel will ignite without the need of an outside ignition source. So the minimum temperature the minimum temperature at which a fuel will ignite without the need of an outside ignition source. So this depends on the physical arrangement of the fuel. So if you heat wood to a given temperature, or gas, or diesel, or plastic, if you heat any of these materials to a given temperature, there's a point where it will light off without having an introduced outside ignition source. So, thermally thick material on the front face will not have a temperature rise on the back. Thermally thick material heated on the front face will not have a temperature rise on the back. I would assume what they're talking about here is, man, they really jumped around on this. Material heated on the front face will not have a temperature on the back. Material heated on the front face will have nearly the same temperature rise on the back. So I would assume that they're talking about, man, that's crazy. I would assume that they're probably talking about like conduction of heat. Um, it's very interesting that they jumped to this point. Um, yeah, yeah. Okay, all right. That's a good point. So what you're saying is that from your perspective they're referring to like surface area here. So like yeah, I could see how that would be what they're talking about. So a good example of that is like in your tree analogy. If we have a tree that is in the middle of a bunch of fuel, it's going to take a lot of off-gassing and a lot of heat to get that tree to light on fire. Whereas if you have a bunch of smaller sticks, like you're building a campfire, like kindling, you would have a much easier time. Thank you, sweetheart. You'd have a much easier time getting that kindling to light off just based on the surface area and the density of that wood. So yeah, that could be what they're talking about here. It's interesting. Probably a better teacher would know exactly how the order of these slides would go in. Yeah, for sure. Very cool. Wow, man. So if you're reading the chapters ahead of time, we're gonna be leaning on you for all kinds of this stuff. Nice work. So surface to mass ratio is exactly what we were talking about. The greater ratio, the easier it is for a solid to absorb heat. Um, the greater ratio, the easier it is to reach its ignition temperature. And the greater the ratio, the easier it is to ignite. So that surface to mass ratio is like we talked about with kindling versus a tree. Um, the amount of surface area that you have to be able to heat that material versus the amount of mass that that material has is gonna determine how quickly or how easily it's gonna catch on fire. So that's what makes that's the main piece that makes grass fires burn much quicker than something that would burn through some trees just based on the amount of surface area that that grass has. Based on this concept, wood dust can be extremely dangerous under fire conditions. Wood dust is on the extreme end of that. It has, a very, very high ratio of surface area to the mass of the dust itself. That's why it can be even to the point where it's explosive. Some liquids, such as water, do not burn, which is good because we need the water to put the fire out. Flammable liquids have a flash point of 100 degrees or lower. The general idea, the reason that the flammable liquids have a lower flash point than the solids is because from a scientific standpoint, it's going to be easier to convert a liquid to a gas than it is to convert a solid to a gas. Maybe a better way to say that would be it'll take less energy to convert a liquid to a gas than it will to take a solid to a gas. So they have a lower flash point. Combustible liquids have a flash point above 100 degrees Fahrenheit. Okay, so flammable liquids have a flash point below 100 degrees. Combustible liquids have a flash point above 100 degrees. So they're categorizing the different liquids between flammable and combustible. Flash point is the minimum temperature at which a liquid gives off sufficient vapor to form an ignitable mixture with the air near the surface of the liquid or within a test vessel. So flash point is the minimum temperature at which a liquid gives off sufficient vapor to form an ignitable mixture with the air near the surface of the liquid or within a test vessel. Liquids must be at their flash point when fuel vapors are being given off in order to ignite. So for a liquid to ignite, like in their case of a grease fire here, the flash point must be met whenever the fuel vapors are being given off in order for it to ignite. So that has to be hot enough because you can have oil, cooking oil on the stove, and you can have it off gas, and you can have it convert to vapor, and you can see it going up before you heat it up to the point where it hits that ignition point, and then at that point, then the fire will create more heat, and then the entire surface area of that pan will be at the ignition temperature. So atomization is the process that breaks a liquid into a mist, yet its physical state is still a liquid, even though the liquid is in finely divided particles. So this is initially where you'll get the, like a carburetor or even fuel injection is initially going to be atomized until it's compressed, and then as it's compressed, then it's going to be turned into a vapor. But um, it is still technically a liquid, it's just suspended in air. Ignitable liquids, when atomized, have a surface to mass ratio that permits rapid vaporization. When ignition source is introduced, the liquid will ignite. So again, back to our internal combustion engine. Ignitable liquids, when atomized, have a surface to mass ratio that permits rapid vaporization. That vaporization happens very quickly whenever you add the compression to the air that it's suspended in. And then ignition source is introduced, the liquid will ignite. So in a gasoline engine, they're going to introduce an ignition source with a spark plug, whereas with a diesel engine, there is no ignition source. They just use pressure to be able to heat that fuel to the temperature that it needs to ignite on its own. Fire point is the temperature at which sufficient vapors are present to ignite and have sustained combustion. So once it ignites, the heat that it's going to produce from its own combustion is going to make sure that the entire atomized fuel or vapor fuel is going to be at above the temperature that it needs to sustain its own combustion. That's the fire point. So the flash point back there is when we can light it off with an ignition source, and the fire point is whenever it's going to sustain its own combustion. So gases, cooled gases can become liquid again. If you have vaporized water and you cool it again, it will go back to water. Propane, nitrogen, and oxygen can also become liquid once they're cooled to the correct temperature. Some gases burn, others do not. Like we talked about, water gas or H2O does not burn. Flammable gases at most ambient temperatures and pressures have already vaporized. Ignition source is needed to start combustion. So flammable gases at most ambient temperatures have already vaporized. Okay, now we're going to talk about some explosive limits. The lower explosive limit is the amount of fuel vapor in the air is below the lower limit. Too lean to burn will not ignite. So, um, in our internal combustion engine, there's a ratio of the amount of fuel vapor in the air that it needs to actually perform ignition. And if it's too lean, if there's not enough gasoline mixed in with the air that it has in the engine, it will not ignite. That's the lower explosive limit. Now the upper explosive limit is whenever there is too much gasoline in the engine, and that would be too rich to burn and will not ignite. So, in an internal combustion engine, we're able to control this with carburetor jetting, but also the choke. Whenever we activate the choke on our chainsaws or our small engines, we're enriching the mixture to get it to light easier. But if we get it too rich and we flood it, and you guys have flooded it before, I'm sure, it will not run because the mixture is too rich, and you have to get the uh, get the excess gasoline out of the engine before it'll get back to a point where we can get it to light off. So the lower explosive limit is the limit of where it's too lean. The upper explosive limit is the limit of where it's too rich. And we can apply both of those limits to all kinds of things, not just an internal combustion engine, but we use those are kind of some of the numbers that we pull off of our uh, our gas monitor when we go on gas leaks. We talk about the lower explosive limit and the upper explosive limit on gas leaks. Same concept. There's a ratio of natural gas to air that will burn, and there's a ratio of natural gas to air that will be both too lean and too rich. And so those are the lower explosive limits and the upper explosive limits that we're looking for. So ignition will not occur if the mixture in air is too rich or too lean, like we talked about. Gases can have narrow and wide ranges. So different gases are going to have different ranges of what's between their lower and their upper limit. So like gas, and again I don't know, but they're going to have different ratios of uh, of gas to air for it to burn. And we're using standard atmosphere air, not pure oxygen. So let's see what we got here. Oh, I would assume gasoline is on the left here. The flammable range of 1.5% saturation to 7.6% saturation is the amount of gasoline versus the amount of air. That's the flammable range. It has a very small flammable range. Whereas carbon monoxide, now that might be backwards. I'm not sure. Any ideas, Tristan, which one you think of these might be gas and which one might be carbon monoxide? That's what I was thinking too. It'll get too rich quicker as well. Yep. Yep, I just looked at my notes here and I found verification for that as well. So gasoline is 1.5% to 7.6%. Anything, and then carbon monoxide is 12.4% saturation to 74% saturation. So um, carbon monoxide is what we would find if we were looking at um, some different situations with furnace problems like we can typically get called to. Um, the lower explosive limit for that is much higher at 12.4%, but the upper explosive limit is up there at 74%. So Again, this is the ratio of the fuel to the atmospheric air. And every gas that we're going to find is going to have its own flammable limit. Propane will have its own range, wherever that may land. Natural gas will have its own range. Diesel will have its own range. But the general idea is that we understand that there's always a lower limit and an upper limit for each given gas type. So consider the following. Atmospheres below the lower explosive limit can be made safe by ventilating. So if we have a situation where we're below the lower explosive limit, we can easily introduce more air, more atmospheric air, and we can drop that lower explosive, or we can drop that saturation percentage even lower. However, if we have a situation where the gas saturation in an environment is above the upper explosive limit, if we ventilate that, we're bringing that we're introducing gas. So like if we go back to, maybe we have somebody's garage and they've spilt gas all over the floor, and all the gasoline all over the floor it has evaporated into the ambient air in the garage, and maybe it's like a 50% saturation. Like you walk in there and there's this gas, like it's above the upper explosive limit, right? So there's a whole bunch of gas in there. Well, once we start ventilating that, it's going to bring the ratio of gas down as we introduce fresh air, and eventually for it to get down to zero, we have to cross through that explosive limit. So that's what it's referring to here, is if we have gas in an area that's above the upper explosive limit and we ventilate it, we will cause the ratio to get into the flammable range. There's no way around that, but that is something that we need to all be aware of. Does that make sense, Zach? Good. So inert gases will not support combustion. Nitrogen, argon, helium, carbon dioxide will not support combustion. Flammable gases will burn. Hydrogen, propane, butane, carbon monoxide. Okay. Um, yeah, they're not going to break that down, but you'll understand that there are certain gases that they're not flammable on their own. Pretty self-explanatory. These are all fuels, right? These are not fuels. We pretty much we pretty much understand most of the things that our community that are designed to be fuels, but we always have these placards that help remind us of what is flammable and what is non-flammable. And we won't get carried away into hazmat today, but we might get into a little bit of it. So meters, like you've all seen our gas monitors. These detect the presence of flammable gases and their percentages in the air. And I don't have our meter with us, but it will give you typically just an LEL, a lower explosive limit, um, and then it'll give us an idea. Now, yep, it's not going to go into that. So what we need to understand is that you know you may look uh, into the book about the hazmat stuff, and you may find that it says gasoline has a lower explosive limit of 1.5%. Now, that doesn't mean that whenever this number on our monitor gets to 1.5, that it's within the lower explosive limit. That means that whenever this number gets to 100, that we are at the lower explosive limit, because this is a percentage of LEL, right? So the percentage of the lower explosive limit. Does that make sense? So what we're looking for is this to be on a scale of 0 to a 100 of the lower explosive limit. So like if carbon monoxide is 12.4%, lower explosive limit, once this gets to 100, that means that we are at 12.4% saturation. So if you see, Don't know. Well, it's definitely not completely different. Um, H2S, lower explosive limit. That's hydrogen sulfide. That's probably not hydrogen. I don't. I don't think hydrogen cyanide is a flammable gas. Yep. So typically, yeah. This does, however, say that carbon hydrogen cyanide does have a lower explosive limit of 5.6% and an upper explosive limit of 40%. So apparently, it does have an explosive limit, hydrogen cyanide, which is interesting. I Yep. 100%. So yeah, so the main concern that we have with hydrogen cyanide, like Tristan is saying, is um, the detriment that it does have on the human respiratory system, which, if I'm not mistaken, it displaces oxygen. Is that correct, Tristan? He muted himself as he was talking. But I'm pretty sure hydrogen cyanide would displace oxygen. Yep, yep. It is pretty cool. I didn't know that. Okay, so chemistry and physics related to fire. Following completion, we should understand the chemical and physical events that relate to heat, the four common sources of that heat energy, the term heat release rate, and the three types of heat transfer. Specific heat is the amount of heat that a substance absorbs as the temperature of a substance increases. The amount of heat required to raise a unit of mass of a substance by 1 degree, and it's measured in joules per kilogram, or Kelvin. The amount of heat that a substance absorbs as the temperature of the substance increases. And the amount of heat required to raise a unit of mass of a substance by 1 degree, measured in Kelvin. Might be a test question. Latent heat is thermal energy that is absorbed when a substance is converted from a solid to a liquid or reverse. So the thermal energy that is used or absorbed, because everything's ever used, it's just transferred, right? Converted from a solid to a liquid. What it takes to melt ice, right? Latent heat of vaporization, the amount of heat absorbed by a liquid converts to a gaseous form. So vaporizing boiling water into vapor. That's latent heat. Water has an extremely high heat of vaporization. It takes a lot of heat to vaporize water, whereas, for example, gasoline has a low heat of vaporization. Gasoline will vaporize if you throw it on the ground at 50 degrees Fahrenheit, whereas water takes what, 212, I guess? Probably 208 at our altitude. Ideal. That's it anyway. That's the reason that water is ideal as an extinguishing agent. Because again, if we go back to our fire triangle, most of what we're doing when we're putting water on the fire is we're removing that heat from that fire triangle. That's so as an extinguishing agent, water takes a lot of heat before it vaporizes. Density is the ratio of mass to volume. I think we all understand density on an inherent level. But it's the ratio of mass to volume is the definition. So if we have something that's real heavy for a given volume or given area, it would be more dense. So lead is very heavy for the amount of volume that it takes up. Lead is very dense. If we have aluminum, it's relatively light for the amount of volume that it takes up, so it is a lower density than lead anyway. High density objects require more heat to ignite than low density objects. So our sawdust or our wood shavings are low density, so they take less heat to ignite than a tree does or a 4x4 here. I think we understand that pretty well. Weight density of a liquid compared to another liquid, usually water. So specific gravity, I'm sorry. So specific gravity is the density of a liquid compared to another liquid, usually water. So a specific gravity of greater than 1, a substance sinks. Specific gravity of lower than 1, a substance floats. So um, oil or gasoline or diesel has a specific gravity that's lower than 1, so those products will always float on top of the water. Whereas if you have mercury. Mercury has a density that's more than water, so mercury will sink underneath the water, right? Here's some examples. Acetone is lighter than water, so you see that it's less than 1 here. Alcohol, ethanol, methanol, and propyl alcohol all have their own specific gravities that are all less than 1. Carbon disulfide has a specific gravity that is over 1, so it will sink below water. We have some other examples here: tartrate tetrachloride, castor oil, coconut oil, cottonseed oil, crude oil, formaldehyde. You see anything that has a density less than 1 means it will float on water. Fuel oil, gasoline, hexane, kerosene, linseed oil. There's our mercury example at 13.6. Good night, dense stuff here. And then milk at 1.0. The problem is typically it's just going to mix anyway, but and then naphthalene, olive oil, toluene, and turpentine. So you can see that most units will have a density less, and most units are going to float on top of water. So vapor density is the same concept, but we talk about it with gases. Compares the density of gases with that of air, greater than 1. Same concept, like we say, greater than 1. And again, as far as I know, these are going to be compared to atmospheric air. Um, so greater than 1 will sink underneath our atmospheric air, and then lower than 1 will rise above our atmospheric air. So helium was a pretty obvious one. We use it in our balloons at our kids' parties. Has a very low vapor density, 0.14. It will easily rise in our air. Whereas if we have, some of these other materials, all of these are less than 1. But like does it have natural gas? Yeah, natural gas is still less than 1. Only 13 gases are lighter than air. I know there's some common ones that we have out there. I was thinking ammonia was one of them, but I am. Can you got anything, Tristan? What's something that's heavier than air? Oh, okay. Sure, understood. Yeah, vaporization. The opposite of vaporization. Or no, vaporization would be liquid to a gas. Solid to a gas would be yeah, something else. We should know it. Sublimation. Sublimation. There we go. I knew it was weird. All right. So the chemistry and physics related to fire, heat, heat transfer, and heat release rate is what we're going to talk about next. Um, Following completion, we should understand types of measurements that apply to firefighting operation, types of temperatures, scales used in fire protection, terms used to describe heat release, right? So heat is energy characterized by the vibration of molecules capable of starting and supporting changes of state, i.e. liquid to gas. So heat is a measurement of energy that talks about these vibration of these molecules that support changing of state. Heat release rate is the amount of heat generated over time, and it's important to understand for fire flows. BTU is short for British Thermal Unit, and it's the amount of heat required to raise 1 pound of water 1 degrees Fahrenheit. So it's a measurement of heat, right? BTU, British Thermal Unit, 1 pound of water 1 degrees Fahrenheit. Joules is the metric scale. Temperature scales, Celsius and Fahrenheit, we've all pretty well gotten these figured out at this point in our life. Water freezes at 32, boils at 212, again depending on atmospheric pressure with things like altitude. Celsius is the metric version, freezes at 0, boils at 100. Chemistry and physics related to fire, types of heat. So we have chemical heat, electrical heat, mechanical heat, and nuclear heat. So chemical heat, combustion is a chemical process that produces heat. So the heat that we get from fire is from chemical heat, from the combustion process. Decomposing matter also produces chemical heat, right? So if you have a bunch of oily rags and you throw them in a bucket, they're decomposing and they're producing chemical heat. If you've had a compost bin and you stuck your hand down in the middle of it, it will produce uh, chemical heat. And that's what gives us our supposed or our self-igniting haystack fires. So spontaneous. Oh yeah, hey look, spontaneous ignition is the ignition of material combusted by an internal chemical or biological reaction. Example is cloth soaked in linseed oil. Oil attacks and breaks down the fibers of the cloths or the rags. Heat is generated and builds up. The ignition temperature is reached and material ignites. So this is the concept, like I talked about with the oily rags in the bucket. Same thing for our haystack fires. If they stack the stuff and the hay is too wet, um, that breaks down the hay, produces more heat. That heat generates and builds up. Hay is so well insulative that eventually that heat builds up to the ignition point, the ignition temperature. Electrical heat is a common source of heat energy, right? Flow of electrical current can generate heat. So any product that uses electricity uses heat or puts off heat as a byproduct. So this computer, our phones, our vehicles, anytime we're using electrical energy for powering electronics, there's always a byproduct of heat. That's what determines the efficiency of the product. So a more efficient product will put out less heat byproduct. Um, a less efficient product will put out more heat byproduct. Electricity flows from a negative to a positive charged location through a conductor. Denser conductors flow more electrons. So copper wire is a good conductor, and wood products are not a conductor, or not a good conductor. They're a good insulator. Now, obviously, the water content of that wood will affect how good it is at a conductor, but for the most part, um, we're talking about density um, and how they can flow electrons. The greater the flow, which is amps, of electricity, the more heat is produced. So the more power we're flowing, the more byproduct of heat is produced. The greater the resistance to the flow, which is ohms, the more heat is produced. So that's where we come up with our efficiency of things, like our efficiency of our televisions or the efficiency of our cell phones is by a lot of it is mitigating the amount of resistance that's producing the excess heat. So wires in a toaster have a high resistance and heat up. That's what produces the heat to toast your bread is by a great deal of resistance, the same way as a baseboard heater would do, or an electric hot water heater. It's using the resistance to produce as much heat as it can for a given for as few amps as possible. Electrical arc occurs when flow of electricity is interrupted, releases heat, a lot of heat, and can reach up to 2000 degrees Fahrenheit. Occurs in light switches or in a down power line. So whenever you flip a light switch, there is a very small electric arc as it bridges that connection, sort of like whenever you hook up the battery in your car, you get a few little sparks. That's the electrical arc. But on a larger scale, a down power line would also produce a very significant electrical arc. Lightning occurs in nature, occurs when electrical charges differ between clouds and or ground. So whenever there's a large differential um, between the clouds and the ground, that's what gives us our cloud to ground lightning strikes. Results in cloud to cloud or cloud to ground lightning. Can produce in excess of 50,000 degrees Fahrenheit. So a lot of power out there in nature for sure. Static electricity. Electrical charge collects on the surface of an object. Charge does not flow until one of the following is present: contact and separation between dissimilar solids, flowing powders, or flowing liquids or gases. So we've all experienced static electricity. When you touch something that has built up a charge, you can get that little shock. Static discharge can ignite flammable liquids and be transferred between containers if they are not both grounded. So static electricity arcs can ignite um, flammable liquids or gases if they're within the proper explosive limits. Induction is the process, um, electrical induction is the process of heating electrically conducting object. Currents are generated within the metal and resistance heats the metal, right? So that same concept as our toasters, ovens, kind of deal. Mechanical heat is actions that develop a sufficient temperature will ignite flammables or combustibles. Friction between two objects rubbed together is the most common example. So mechanical heat um, is typically the most common is friction between two objects rubbing together is creating a mechanical heat, whether it's Tires on the road, as the tires roll over the road, that would be a mechanical heat. This dude's grinding an axe. Those are producing a mechanical heat. Um, things like that. Examples of friction. We understand friction pretty well, right? Metal parts rubbing together with no lubricant. Lubricant will decrease friction. Metal object being sharpened by a grinding wheel, right? So it will obviously produce heat based on friction. Everybody understands that at this point, I'm pretty sure. Now, compression is another type of mechanical heat. Compression under pressure at a rapid pace. Just like this is a good example when we fill our SCBA cylinders. If you fill them even at a moderate pace, you will notice that the bottle will heat up, and that's a byproduct of compression producing off a mechanical heat. To the extreme would be like an internal combustion engine, particularly a diesel engine, is going to give off a lot of heat with all that compression, and that's what gives us our ignition point. Nuclear fission. Splitting of the atom generates energy. Early atomic bombs and nuclear reactors. Creates nuclear waste as a byproduct. I don't have a lot to add to this. I don't know a lot about nuclear fission, but hopefully we never have to fight any fire like that. Fusion is fusing of atoms generates energy. Stars have fusion reactions, generates little or no nuclear waste, not used commercially, difficult control. Well, that's what we need to start figuring out. Get some nuclear fusion going. Requires special equipment and training to fight fire involving nuclear materials. I don't think we'll have to worry about that here. Never attempt to fight a fire with radioactive materials, no matter how small the quantity. So even if we have some kind of oil-filled truck that wrecks with some nuclear materials on board and there's nuclear placards all over it, we probably ought to call somebody that knows more about it than we do. Structural PPE provides no protection. That's right, those guys at Chernobyl still had a rough time. All right, chemistry and physics related to fire, the heat release and transfer. Heat transfer. Heat release is a byproduct of fire, is transferred to other objects. Yep, transfer of heat passes from a hot object to a cooler object. We're going to talk about the different ways that heat will transfer, but thermodynamic laws are going to say that typically heat's going to transfer from a hot object to a cooler object. Just like in the atmosphere, just like in a cup of water. I imagine we're going to talk about this quite a bit here. So, factors in heat transfer. The material's ability to retain heat. Time is a factor. Material type and combustion, and distance. So all these things are going to factor in to how quickly or how much of the heat is transferred, right? So the three most common methods of heat transfer are conduction heat, convection heat, and radiation heat. Okay? So conduction heat would be if you have a hot pan that you have on the oven and you grab the handle and the handle is hot, that's because the heat has used conduction to travel through the pan and through the handle down to the point where you touched. Convection heat is the actual heat that's being put off from the burning itself, that's the gases and the flame. So the convection heat I always think of as being the actual flame impingement itself. And then radiation heat is going to be like what you feel when you're sitting around the campfire. That's the radiation heat. That's that heat radiating out from that combustion process. So, conduction heat. Heat is transferred by direct contact between objects. Direct contact. Fire can start in a remote area if flammables are touching an object, conducting heat from the original fire location. So if you have maybe some apartment complexes and they've got some steel beams, you could definitely get heat transferred through that steel beam they could transfer between a compartmentalized location. What they have here looks like a warehouse situation. They're showing that there's a fire over here. Um, it is heating up these beams. The beams are heating up through the wall, and they've got some boxes stacked up here. So thermal conductivity directly related to the mass of the object and the quantity of heat released. Heavier, denser materials are better conductors. So steel is typically what we think of when we think of conduction heat, but obviously anything that's dense, copper, any type of metal for the most part, is going to be a good conductor of heat. Metals are excellent conductors. Yeah, there you go. Conduction. All matter is thermally conductive on some level. Now, some levels are better insulators and some matters are better conductors, but they all will, to an extent, thermally conduct. Materials with low thermal conductivity make good insulator, like gloves. Materials with high thermal conductivity transfer heat, like most metals, based on a density or mass to volume ratio. We've talked about density, right? Which is, again, a mass to volume ratio is the definition of density. Transfer of heat via fluid or a medium, convection. Convection is the transfer of heat via a fluid medium. Can be liquid or gas. So convection heat, they're talking about a lava lamp here. Um, Natural current, this looks like a smoke and fire. Going out through the roof would be their convection heat. Less dense will rise. Warm air or liquid is less dense and it will rise. Cool air or liquid is more dense and it will sink. This is the basis of weather on the planet Earth, right? Cool air is more dense and it will sink. Less dense or warm air is more dense. I'm sorry, geez, is less dense and it will rise. So whenever we have our thunderstorms, that's because the warm air is rising quickly. As it rises in the atmosphere, it takes moisture with it, um, and that's what gives us our vertical convection, vertical development. So, flames and heated gases passing over a material will transfer heat through convection. So, as the heated gases and the flames pass over a material, whatever that material is, they're going to transfer heat through convection. Many objects are ignited this way. So, if you start a fire in the bottom of your burn barrel, you notice very, very quickly that the fire will burn up. That's because heat rises, right? So, if you start the fire at the bottom of your campfire, it will very quickly extend up. If you start the fire at the top of your burn barrel or your campfire, it will take a long time for it to burn down. That's because the convection heat, heat always rises, and it will take a lot more time for it to burn downward. Heated air in a closed container will rise to its highest point. So if you have a closed container, their example here is an office building. It's going to rise to the highest point. We know that heat rises by now. Equilibrium is achieved when the air reaches the same temperature of the surrounding atmosphere and upward movement stops. So once we get to the point where all the air within our fire room, within our room and contents fire, it's all reached the same temperature. There's no more upward movement because the upward movement is driven by a temperature differentiation. Whenever there's no differentiation in the temperature, whenever the temperature is all the same, there's no more upward movement or there's no more vertical development. Pressure increases in the container when heated. Okay, higher pressure moves to a lower pressure. Ventilation removes heat and smoke. So as it's building pressure, that pressure is going to want to equalize and it's going to want to move to a lower pressure area. Um, especially outside the building. So it's going to do everything it can to get outside the building. That's why as you pull up to a fire that's inside of a house, you'll see it pressurized and pushing out of the soffit vents or out of the eaves of the house because it's pressurized. It's a higher pressure. It wants to move to a lower pressure area. Same principles apply with a fluid. So heat absorption, the fluid absorbs heat, vapors are given off, vapors rise to the top. That's our boiling water. So that's convection heat. A BLEVE is a boiling liquid expanding vapor explosion. That's the process of a BLEVE. Is fire impinges on a cylinder containing liquefied flammable gas. Since it's in a cylinder, um, it's in a confined, sealed um, device, and it's building pressure as it heats. Since it has no way to ventilate that pressure or escape that pressure into the outside world, eventually it will get to the point where failure of the container will release all that pressure instantaneously, right? That's what a BLEVE is. So we have a fire underneath a propane tank. It's building the pressure inside that propane tank. Ideally, it will relieve that pressure through the pressure relief valve on top of the tank. However, one of two things can happen. Either it can't relieve the pressure as fast as it builds, or the valve fails, in which case it will continue to build pressure past what the cylinder can contain, and a BLEVE would be the process of that cylinder exploding. Okay. So, radiation heat is the transfer of heat through space by light waves. Energy absorbed by objects remote and in direct line with a fire. So, in order for you to have radiation heat, you have to have direct LOS or direct line of sight with the fire. So, if you're standing in front of a campfire, or even if you're on the scene of a structure fire, you put your hand in front of your face. You don't have direct line of sight between your hand and that fire, and you instantaneously shut off that radiant heat from your face. You guys have all experienced that, I'm sure. Radiant can travel through open space, through clear glass, and through water curtains. Radiation is expected by the size and distance to the burning area. So the farther you are away from that, whatever it is burning and putting off heat, the less heat that will be transferred. As target objects absorb radiant heat, they begin to give off their own radiant heat. So radiant heat is always happening on some scale over any given distance. If you're 100 yards away from a fire, there is a measurable amount of heat, depending on the amount of heat that's being put off from that fire. If it's a campfire, you probably won't feel it. Whereas if it's a group of trees torching on a wildfire and you're 100 yards, that's too close. That's unbearably hot. Whereas like our sun is, I don't know how far away our sun is, Tristan, but it's very far away, right? But it's putting off a shit ton of heat, and so obviously we still feel that radiant heat through all that distance. So the distance affects the amount of heat, but it does not negate it entirely. So the heat release rate is the amount of heat energy released over a period of time. Heat release rate is the amount of heat energy released over a period of time, measured in BTU per second or measured in watts. Examples of a 100-watt light bulb, a 100 megawatt nuclear reactor, or a 10,000 BTU air conditioner. The amount of heat released over a period of time is the heat release rate. Sounds like a test question. Heat release rates, this is where we talk about how much fire behavior has changed over the course of the past X amount of years. And this is a lot of what drives that, right? So if you have a chair that's upholstered in polyurethane foam, we're looking at 2100 kilowatts. If you have a chair PVC waiting room with metal frame, I guess maybe they're talking about like a little folding chair or something, is going to be closer to 270 kilowatts. Metal frame with polyurethane padding, this would probably be like a folding chair, 40 kilowatts. So you can see that the amount of, typically it's going to be driven by cotton, or I'm sorry, it's going to be driven, not red cotton, it's going to be driven by plastics. It's going to be driven by things that are made with oil and different plastic stuff. That's what's going to drive the main component of heat release rate that we see in residential fires. And so the more, like here you have a mattress made out of cotton way back in the good old days, might be closer to 40 to 970 kilowatt, whereas this one says polyurethane foam, like the memory foam mattress that most of us have is going to put off an absolute shit ton of heat when that thing burns. Like we're talking like pure gasoline. Um, so the products that we have, yeah, what's up, Zach or Tristan? For sure. Yeah, see if I know there is a bunch of UL studies and stuff like that on there. See if you can pull something like that up and send it to me while we're talking here, and we'll see if we can watch something like that because there are some very valuable videos that we can watch here for a minute. So yeah, see if you can find something like that, Tristan. So heat flux, the rate of heat energy transferred per surface unit area. Examples, a heat flux of 20 kilowatt means every square meter of the floor below the hot ceiling smoke layer is receiving 20 kilowatts. So a heat flux of 20 kilowatts means every square meter of the floor below the hot ceiling gas layer is receiving 20 kilowatts. Okay. So, smoke. Definition of smoke: the airborne solid and liquid particulates and gases evolved when a material undergoes pyrolysis or combustion, together with the quantity of air that is that is entrained or otherwise mixed into the mass. So, smoke is the airborne solid and liquid particulates and gases evolved when a material undergoes combustion. What's up? Find one? Email. Kyler.massey at brushfd. All right. Finally finished my taco. I imagine so. There's a bunch of them out there. So there's a number of things at play there, right? One is the ignition point of those synthetic materials is lower than cotton. Like
G'day everyone, my name's Matt, and
it takes quite a bit to get cotton to burn, whereas the ignition point to those synthetic materials is lower. But the other component to that is, like we talked about, the heat release rate. So the amount of heat that those plastics put off, those synthetics put off when they burn, is exponentially more than whenever cotton burns, right? And so that gives us an exponential growth, because not only is the material lighting off at a lower ignition point, but it's also putting off more heat when it burns, and that's what exponentially causes it to ignite more rapidly. Um, it is very interesting. It's uh, it's one of the largest components when it comes to talking about fighting fire these days versus 50 years ago. It was a big shift for a lot of those guys at that time period, because relatively speaking, it happened very quickly when we went from the average home being filled with cotton products, um, to whenever the synthetic age became more affordable and cheaper. It happened within the span of 5 years. Everybody had 10 years. Everybody had replaced all their furniture, and so it was a bit of a learning curve for some of those guys in that generation, especially whenever if um, you don't really see it now, but you would you would 40 years ago, 30 years ago, even 20, 25 years ago, you would talk to a lot of the old firefighters that just absolutely did not see a need for wearing an SCBA inside of a structure fire, and a lot of that came from that mindset that, like, what the stuff that's burning is Class A materials. Just like when we go on a wildfire, like, we don't wear SCBAs on wildfires because for the most part, they're Class A materials. And whenever we got to the point where we were burning synthetics, it would have a very detrimental effect on a lot of those guys' lungs, and that was what the initial push for the cancer problems that we had in the fire service was getting guys to understand how that had evolved. But it's just really interesting how fast that the fire service had to really adapt to those large changes and what was inside all these homes. Okay, so we talked about the definition of smoke. It's basically suspended particles, particulate. Components of smoke, we have carbon, particles, or soot is the main solid particulate. Carbon is the main component of smoke. Liquid particles include condensed tars and water vapors. Multitude of gases, including carbon monoxide and our good old boy hydrogen cyanide. So the components of smoke, primarily carbon, primarily unburnt fuels, right? Primarily carbon particles or particulate. There is some liquid. There's always going to be a component of liquid. That's what gives us our humidity in our air. So there will be some liquid, um, and more or less depending on a multitude of factors. And then there will be a bunch of different gases like carbon monoxide, hydrogen cyanide, etc. Hot smoke at ceiling level plays crucial role in development of a flashover. Smoke can become explosive under the right conditions, resulting in a backdraft. So that's why we talked about, whenever we go into a fire, we talked about sweeping. Last week when we were doing this, we talked about sweeping the ceiling. We want to keep those that smoke at the ceiling level, keep it cool, to help deter a flashover situation. So that's why we always want to make that a good habit. We go in, we don't want to get fixated on that fire on the floor, because we can see all that heat has all risen to the ceiling level, and the ceiling and that smoke could be at the point of the ignition point of that smoke. Once all that heat and that smoke at the ceiling, once it gets to that own ignition point of whatever's in that smoke, that's what gives us our flashover. So we want to be cognizant of that, and we want to keep that upper level cool. Compartment fire development. This is our standard room and content stuff. We're going to talk about the 4 stages of fire development. We're going to talk about flashover, rollover, and backdraft. So all fires have a distinct pattern of growth. We have the ignition point, we have the growth stage, the ignition stage, we have the growth stage, we have the fully developed stage, and then we have the decay stage. This will 100% be a question on the test. Ignition stage, growth stage, fully developed stage, and decay stage. Fuels must be heated enough to emit ignitable vapors. Okay, we've talked about that. The fuels have to give off their vapors in order for them to actually burn. Gases and liquids ignite faster than solids. We talked about that. We talked about how gases and liquids will evaporate at a more rapid rate and at a lower temperature than solids will. First stage, ignition. Ignition source unites with ignitable vapors in an oxygen sufficient atmosphere, 21% to 20%. Fuel supply is adequate, so we're within that, that explosive limit or that flammable limit of what it takes to have the right ratio. And typically the fire is small and limited. So typically in the ignition stage, we've got a pretty small fire. But it rapidly changes into the growth stage, which is the second stage. Fire growth is self-sustained, so it's putting off enough heat through radiant heat, convective heat, and conduction heat to where it's preheating the other materials around it to their ignition point, and it's self-sustaining fire development and growth. Objects on fire transfer heat to other objects, which in turn begin to ignite. It's going to do that through our 3 methods of heat transfer: radiant, conductive, convective. Entrainment is the process where the air is drawn into the fire. So they're giving a name to it, but basically what that means is we're drawing air. That fire is growing. That fire is giving off a lot of vertical pressure and a vertical development, and it really wants to put all those super hot gases. As it does push all those super hot gases upwards, it has to replace everything that it's displacing. It creates a low pressure environment at the fire itself, which draws in air from everywhere around it. On a large scale, you can relate this to wildland fires. You have a column developed, you have a large vertical development. That fire will, vertically develop that column. You'll see that great big column on the news and all the pictures. Well, all the way around that wildfire, all the air is being drawn in towards that fire at 10 to 15 miles an hour. A lot of pressure bringing all that fire in. So you can really understand how something's got to replace all that vertical pressure. It happens on a micro scale too. That's why if we have a small fire, you open the door. Depending on the conditions, sometimes you can see that smoke. As soon as you open the door, that smoke will kind of wisp its way and kind of take you towards the fire. If the conditions are correct, you have the right ambient temperature, you have the right number of factors to where you can watch that smoke bring that fresh air. As you bring that fresh air in with the door, it'll show you where the fire's at in some cases. So factors influencing growth. Oxygen supply is a large factor, one of the primary, some would say, that influences the growth rate of the fire. 16% or greater is ideal. In a compartmentalized fire, and I'm sure we'll get to it, but eventually, as you burn fuel, you burn oxygen, it's going to, if it's not self-ventilated, if you don't have an open window or an open door, it's gonna starve itself of oxygen relatively quickly before it starves itself of fuel, typically. But Available fuel supply is also a factor. There needs to be ample supply. It needs to be in a ready physical state, and it needs to have the proper heat release rate of that fuel supply. So it does need fuel. It's just usually there's plenty of it available. So within the second stage, still factors influencing growth. Still size of the area or the compartment, whether it's a small bedroom, whether it's a closet, whether it's a living room. Um, Large space with little fuel limits growth. So if you have um, a warehouse with a bunch of non-flammable materials, it's going to be pretty hard to get that fire to grow. Small space with same fuel promotes growth. Obviously, there's going to be a larger concentration of fuels, more density. Density is probably not a good word, but more concentrated of fuels in a small area. You're going to have an easier time with promoting growth. So insulation of compartment, more insulation, less equals less radiant heat loss equals increased in burning. Less insulation equals greater radiant heat loss and less heat to increase burning. So if you have a heavily insulated room, that radiant heat is going to heat that room faster than if you have a room in like a empty steel building where it can radiate that heat out of the room. So you know it's important to really understand that as a fire burns, the amount of energy that a fire puts off for a given fire, whether it's a single ball of gasoline or whatever, the amount of energy that fire is going to give off is pretty well set, right? There's not a whole lot of variable in there. But what can change is, like we're talking about here, the size of the area of the compartment, as well as the insulation of the compartment, is going to determine how much of that heat that its given fuel is able to maintain in that small area, if that makes sense. So within the second stage, still heated gases rise, which gives us our thermal layering. If there is no vertical opening, it's going to keep continuing to rise. Heat's going to rise until it starts to work its way back down. Um, Hotter gases will always remain at the top because heat always rises. Cooler gases stay near the bottom because, again, heat always rises. This example that they have here, they've got 2,000 degrees at the ceiling, 1,500 degree layer below, 1,000 degree below, 800 degree below. So the heat that is produced from the fire is always going to rise. And then as it heats up from the ceiling down, the heat level is going to keep getting warmer and warmer down towards the floor. So after quite some time, if it doesn't self-vent, eventually the entire room, down to the floor, will get to be um, the same temperature or close to it, right? But by that, is the room itself would not be able to contain that much heat. But the idea is that the heat will always rise, and as more heat is produced, it's going to work its way down from the ceiling. But for the most part, we understand that the hot gases are at the top and the cooler gases are at the bottom. That way, when we go in, we know we need to solid stream the ceiling because we need to cool off that 2,000 degrees Fahrenheit to lower our risk of flashover, right? And we know that down here where we're at waist high, the lower we stay, the cooler it's going to be for us, and the safer it's going to be for us. So, the third stage, which is the fully developed stage, fire has involved the entire compartment. Okay, so the entire compartment is on fire. We're in the fully developed stage. Oxygen level 20 to 18%. We have an adequate fuel supply, so it's free burning. It's getting after it. Watch for the following during the fully developed fire stage. This is where we'll get our rollover, our flashover, and our backdraft. Okay, and I think we'll talk about these here. Rollover or flame over occurs as heated fire gases and smoke rise to the ceiling and ignite. Flames can travel at ceiling level behind firefighters, blocking egress. So we know that heat rises. We know that our smoke is mostly contained of carbon and unburned fuel. Um, so a rollover would be as these gases and these heat as these gases and this smoke get to the point where they ignite and you'll see them start to roll fingers over the top. And we can see this part pretty easily within our training center. It is kind of hard to do with Class A materials because the density of the smoke that a pallet gives off is not the same black density of smoke that we would get burning somebody's plastic couch. So unfortunately, it is hard to replicate, but you will definitely see the concept. Um, Rollover contributes to fire spread, making investigations more difficult because we're in a stage where we're getting, you know, a fluid fuel that's burning. May appear as multiple points of origin. Okay. Flashover occurs as all materials ignite simultaneously. Upper thermal layer reaches 900 to 1100 degrees Fahrenheit, changed from a fuel controlled fire to a ventilation controlled fire. As fire grows, unburned fuel heats up and begins to burn. So, as the fire grows, our unburned fuel that goes up to our ceiling heats up and begins to burn. Same concept as you'll notice with all these. Um, it gets to the point where we've sustained enough heat in the compartment to where everything just goes ahead and lights up. Everything that's off gassing gets to the ignition point. Once something starts to self ignite, um, then it's kind of again exponential growth because it puts off more heat, and everything will for the most part simultaneously light off. That gives us our flashover. Flashovers are deadly to both civilians and firefighters. Firefighters have only seconds to escape, even with full turnout gear. So once we see the signs of a flashover, which again is a rollover is a good sign of a flashover. You can see a high density of smoke at the ceiling. You can see that it's getting to the point where um, the ignition point of that smoke is starting to self-ignite. You'll see the little fingers roll over along the ceiling, and we're getting very, very close to that point where everything will light off on its own. Once it gets to the point where whatever concentration of gases will light off there, that puts off more heat, which lights off more gases, which puts off more heat, and that's what gives us our chain reaction for our relatively immediate flashover growth. So the important thing is to be able to recognize those signs. And even if we're not seeing the signs, that's why we always make it a good habit to always hit the ceiling. First thing we do, we go into a room and contents fire. We hit the ceiling with our pencil line because we don't want the ceiling to be hot enough to be um, at that level where it can self-ignite. We will beat that in forever. Flashover warning signs. Here we go. Flames licking overhead, like we talked about. That smoke is to the ignition point. Rapid heat buildup. Smoke gases being emitted from objects. Flames emerging from doors or windows. So if you're looking around a room and you see curtains and couches and chairs, um, they're all we've hit to the point where the synthetic materials and the plastics and the polyesters are all starting to off gas, visibly off gas. Um, there's a pretty fine line between all the materials off gassing at the same time and all the off gassing being at the ignition temperature at the same time. So once you see all these materials off gassing visibly, you know that it only takes a few seconds for it to go to where all these materials are at their ignition point instantaneously as well. So we want to look for these flashover signs. Now, a backdraft or smoke explosion is we have adequate fuel and heat. We've got heated gases. Again, that's our common denominator, is gases at the ceiling that are getting good density. You know, they're thick black smoke, and they're starting to hit their own ignition point. Oxygen levels are below 16%, so we're in a fire that's relatively starved for oxygen. Our fire tetrahedron is incomplete. We're not getting very good burning. We've just got some real dense, thick, nasty smoke. And we open the door, we give it a sudden influx of oxygen, and that's the piece of the tetrahedron that it needed to continue combustion. The only difference is that the entire volume of the room is ready to continue combustion, and it can occur with an explosive force. So all this gas that's in this room, all this smoke that is at the correct temperature. It's got the fuel that's in the smoke. It's ready to go. The only thing it needs is oxygen, and it's all going to get that oxygen at the same time, and it can give us a very explosive force when it lights off. Backdrafts have blown emergency responders away from entrances of buildings, lifted buildings found off foundations, and hurled persons across the street. Whoops. So we will we're getting pretty close to the end of this here, and we're pushing 2 hours pretty hard. But let's see what we can figure out about. I haven't looked at any of these, so if they suck, I'm sorry. But here is a rollover demo. These guys are in a training center.
That's pretty insane, man. It's awesome.
My bad. All right, so we can see it here if we go back to the beginning of the video. Again, they're in a training center, so they're burning Class A materials, so it's not quite as obvious. Whenever you have thick black smoke, it's obvious. Like you look at the ceiling and you're like, oh shit, dude, like that looks like it wants to burn. But you could see the fuel hasn't changed. The fuel load is still clear back there in that room, right? But you can see that, we're starting to get to the point, and you can see it progress very quickly right there. It starts to light off the heat and the smoke and the gases at the top, and then it just builds. It just builds off of itself. It gets that exponential growth, and it burns clear over here. Now, obviously, I mean, look at that. I mean, it is a very good example. Obviously, it's not burning the fuel from the fire because that fuel is still clear back over here. It's burning all of the smoke and the gases that has hit the correct ignition temperature that's at the ceiling because all the heat always wants to rise, right? But it's all hitting its ignition temperature at the same time. And so it's giving us a rollover. So that's a pretty cool video. Good demonstration. This one might be in an actual fire. I think these guys are training, but this is definitely in some more realistic. Oh man, look at that. So you can see they've got some pretty black smoke up there, right? And it's just hit the temperature. Yeah, these guys are kind of screwing around. So what we want to do to be safe, these guys are training and they're wanting to get some good video footage, which is awesome because we really need some stuff like that. But we want to be cool and not sealing off right now. We don't want that stuff behind us. We don't want it over our heads. We don't want it behind us. Um, Man, that is cool. I think it's ripping. Oh, I'm terrible with numbers. I have no idea. A couple thousand degrees wouldn't surprise me a bit. I don't know. It definitely could be. All right, let's look at some flashovers. Acquired structure burn. That escalated quickly. Wow. And they did that with pallets. I think the carpet was a lot of that. No, because they got hardwood floor. They just managed to get that thing. That's pretty impressive. Oh, I see. They've got the cabinets all stuffed full of. I see. They've got the cabinets all stuffed full of hay. But yeah, you could see that smoke is what's burning. I mean, that just got like, and what really, oh, Jesus. What really drove this was just the rapid development of the heat, right? You know, there's just so much heat being put off in such a short amount of time that smoke has to burn. Like it's got to burn now, just based on you know the laws of physics. You know, once it hits that ignition temperature, regardless of what that smoke is consisting of, it has to burn if it has the materials that it needed. And it had plenty of oxygen there. That was actually pretty crazy. Here is here's a couch 1 minute in. Yeah, so these couches are going to put off, you can see it off gassing. There we go. Let's back up a little bit. So you can see there's built up quite a large smoke layer. There's a lot of heat up top. There's a lot of unburned fuel.
Okay, now watch the material across the couch. You'll
Oh.
see that the material will start melting and deforming as the heat comes down. When that material starts deforming, it's giving off gas vapor that will ignite. Now look up at the ceiling. You see the smoke burning at the ceiling now. So we're at about 1,000 degrees at the ceiling. And at this point, it's igniting see the little chair catch on fire? Go, 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 guys. Notice the carpet's on fire. There was nothing burning on the carpet. The carpet was heated up, began giving vapors off that will ignite, and when it went to 1150 degrees, it all ignited. Okay, go ahead and knock it down, guys. So we hope that seeing is believing. Okay? We hope that seeing is believing.
When you first notice the fire, do you make any attempt to try to put it out yourself?
We would prefer you not, unless you've had some training with a fire extinguisher and have it immediately available. We've had 2 fires in Oak Ridge where they attempted to fight the fire themselves before they dialed 911. So by the time we got there, their house was fully involved. So we prefer you exit out of the house, dial 911, do not go back in.
Very cool. All right, let's see what we can find. What's up? Mm-hmm. Exactly. Which brings us to a backdraft. So you can see, like Tristan's talking about here, you know, there's just not enough oxygen to sustain combustion. And right there, it just happened to have got it.
A plastics factory goes up in flames in Lima, Peru. As thick smoke billows in the air, locals move their belongings away from the danger. Water's having little impact on the blaze, but firemen struggle on. Two men on an aerial platform tackle the worst of it. Suddenly, swirling clouds of smoke swallow them up. They can't breathe.
See how
Desperate for air, they
it looks
crouch down.
pressurized? It's pushing harder.
It's getting too dangerous, so the basket is lowered. The firemen
Look at
turn the
that.
hose
Oh
off for
my
just
gosh.
a second. The force of the fireball knocks out the camera. When the picture comes back, there's total panic. Colleagues rush to help the injured men and drag them away. One of them shows no signs of life. They tear off his breathing apparatus and he's carried away for urgent treatment. The ferocity of the fireball is terrifying. It's hard to imagine anyone surviving, but survive they did.
Oh shit.
About halfway through the living room, me and my partner heard a boom, and then the ceiling fell.
A backdraft is caused from some type of combustibles burning the house and depletes the oxygen inside the structure. But because you've removed the oxygen, they can't burn. So once you introduce oxygen back to it, it explodes out in a violent eruption.
Hmm. So, this is the one. This one right here? Yeah, I've seen this one a couple times. It blows the whole wall down. So this would be balloon frame construction, and we'll talk about that when we get into our building construction, but that's why it blew that whole wall off like that. Then we sounded the evacuation horn. And you notice that it always exponentially increases the pressure that smoke is under right before it explodes, and it's hardly enough time to react. But you see it push out the eaves, and it pushes out the windows right before it goes. Yep. Pretty cool. Well, not that cool, but kind of cool. Fourth stage is our decay stage. Just the fire is diminished, the heat release rate has dropped, and the oxygen levels are typically below 15%. Glowing embers and no visible flames. All phases may be seen simultaneously, such as in a high-rise fire. As fire burns on the floor above is preheated. Sufficient vapors are emitted, and ignition occurs on the floor above. The fire on the original floor continues until the fuel is consumed and enters the decay stage. However, the fire on the floor above would, potentially be in the growth or the fully developed stage. Explosions. We should understand the term explosion and types of explosions. The sudden explosion definition: the sudden conversion of potential energy, chemical or mechanical, into kinetic energy with the production and release of gases under pressure or the release of gas under pressure. These high-pressure gases then do mechanical work such as moving, changing, or shattering nearby materials. Explosion categories. Deflagration. Deflagration. Flame front and pressure wave travels slower than the speed of sound. Natural gas main or dust explosions. We should probably try to retain these. Deflagration, slower than the speed of sound. Natural gas main or dust explosion. Detonation, flame front and pressure wave travels faster than the speed of sound. TNT explosion, more destructive force than deflagrations. Obviously, we've got the more speed. Okay? Deflagration and detonation. Flow path and today's compartment fires. 5 pages left here. Pressure. Fires create pressure, and pressure moves from high pressure to low pressure. Pressure will always move from high to low. The low pressure is any opening that is created at a distance away from the fire. When such pressure differential is created, we have the making of a flow path. So as we open the door, we're creating a low pressure area, and that gives us our flow path. If we stop or control the air from being drawn into the fire, we reduce the temperatures and we slow the combustion process. So that's the reason that we don't want to ventilate until we have the team that is ready to attack the fire. Because if we ventilate before we're ready to attack the fire, all we're doing is growing that fire more before we're ready for it. So here's the example of ventilation limited fire. Our graph has temperature as the vertical and time as the horizontal. We have our ignition stage. We have our growth stage. Decay begins as oxygen is depleted. So it goes into the decay stage. So our temperature goes back down. Change in ventilation allows oxygen to reach the fire. So it could be a self-ventilation. It could be the police getting there and knocking all the windows out and opening all the doors. But it gives it the oxygen that it needs. And so then now we're back on the growth. We're back on the up for temperature. And we get to fully developed. And then as the fuel is depleted, then our decay begins again. So you could see that whenever we start to lose intensity based on oxygen, it loses intensity faster because it loses the oxygen relatively quickly, whereas whenever it loses the fuel, it decays at a slower rate. So tactics. Interrupting the flow path involves tactics that are innovative and sometimes counterintuitive, but fire research shows that these methods can reduce heat within the structure, minimize the potential for flashover, and greatly enhance the safety for firefighters. So they're not going to talk about it. One thing that we can do to interrupt flow path is vertical ventilation, horizontal ventilation. Both those things will interrupt the natural flow path, right? We can also do something where they may be talking about when they refer to innovative and sometimes counterintuitive. But for a while, the fire service was on a large push for something called positive pressure ventilation. And there are still some departments in the United States that are real into positive pressure ventilation. But the basic concept was that whenever you would ventilate, you would coordinate with the team at the front door. So you would make entrance or you would open the door. Whenever you were ready, you would call somebody to knock out usually a horizontal ventilation. They would knock out a window in the bedroom. At the same time, somebody is going to use that ventilation fan like we carry to positively pressurize the house or the whatever the flow path would be. As long as that one window that you broke to that fire is the only exit for the air to go out, and you're pressurizing the house with a positive pressure from the door, you're quicker, you're faster, evacuating the heat and the gases from that fire, and that gives gives you a cooler route to the fire, and it should ideally keep that fire from advancing towards you as you advance towards the fire. But you are also putting more air onto the fire, so if you don't have good coordination, or if maybe it has self-vented into the attic, it can create some problems as well. But it is definitely a common tactic that people have attempted to adopt and train on would be positive pressure ventilation, if you ever hear that. Okay, so in summary of the evening, the fire triangle and the fire tetrahedron, we've talked about that. I think we understand that pretty well. Again, the tetrahedron adds to the triangle the sustained chemical combustion process, chemical chain reaction, whereas the fire triangle would be heat, oxygen, and fuel. The tetrahedron will add the sustained chemical chain reaction. We talked about fuel characteristics. We talked about solids, liquids, gas. We talked about the types of heat. We talked about conductive heat, radiant heat, convection heat. We talked about flammable and explosive limits, the saturation limit that we have of a gas that will be conducive both to flammability and to explosive limits, with the lower explosive limit and the upper explosive limit coinciding with lean and rich, if you're familiar. We talked about the chemistry and physics related to fire. We talked about compartment fire growth and development. We talked about the classes of fire, our incipient stage, or our ignition stage, our growth stage, our fully development stage, and our decay stage. We talked about our methods of extinguishment, which is primarily with water, but we also talked about how we can remove fuel, we can remove oxygen as well. We talked about explosions. We talked about how deflagration would be below the speed of sound and would be like a dust explosion. And we talked about detonation, which would be above the speed of sound, which would be like a chemical explosion, like TNT. We talked about flow path and how we can alter it with horizontal ventilation, mechanical ventilation. We didn't talk about hydraulic ventilation tonight, but we've talked about hydraulic ventilation in other nights. How we can demonstrate that when we get into our live fire, which I think we'll probably try to put some stuff together this week. I don't know if we'll get to. I don't know if we will. I think what we'll probably do is we'll probably this coming Tuesday should just be a regular old training night, right? The day after Christmas. Oh, what do you think guys will think of that, man? You guys want to train the day after Christmas, right? All right, perfect. So what we'll do this Tuesday is we'll do some fire behavior stuff. So we'll get in there, we'll build some fires, we'll watch their development, we'll talk about the different stages. We'll talk about the ignition stage or the incipient stage. We'll talk about the growth stage. We'll talk about the fully development stage. We'll be able to see how it starts to burn those gases and smoke, those fingers that it'll burn up at the ceiling. Um, we'll talk about, and we'll put some water on the fire starting at the ceiling. We'll cool that ceiling off. We'll probably screw around a little bit with some fog pattern stuff. To give us kind of an idea of why we won't get too carried away because we don't want to burn anybody. But we should be able to, give it a quick with a fog pattern and instantly understand why we don't want to do that. Because you will feel the increase in temperature as it evaporates all that water instantaneously. And then we'll demonstrate how we can control the fire, and we can control things with ventilation. And then we'll do some stuff with hydraulic ventilation. But basically, we're just going to spend the evening, kind of watching the development and trying to bring it back with what we talked about tonight of how fires have developed and how we can control them as they develop. Um, and then the next training night that we have, we will kind of put together what we did 2 nights ago, where we would get off the truck with our evolutions and we would make entrance and we would simulate putting a fire out. After we get our live fire going this next week, we should be able to the following training night. We should be able to get into doing some evolutions with live fire with extinguishment. So that'll roll into those pretty well. I think that'll be a kind of a good progression. Unless something crazy happens, that'll be our plan. Which, anything could happen. We could get a big old car wreck that night or structure fire or something, and it all goes to hell anyway. But that's the general idea. Is that we'll work on fire behavior on Tuesday and see if we can't learn something. Yeah. Yep. Cool. Well, thanks, guys. Appreciate you coming. I'll have a quiz together. I actually, let's see. Did you guys do the quiz? No? You guys didn't do the quiz? Oh my gosh. Jeez. 0 responses? What the hell? That's all right. That's all right. They're not going anywhere. They're not going anywhere. But again, we'll keep pushing forward. So there will be a new quiz tomorrow. You guys will be double behind. So I'm sure you'll figure it out. I'm sure you'll figure it out. Okay.